Okay, so alcohols contain an OH group, and we call that OH a hydroxyl group. So this is what they look like as a functional group. We've got the OH bonded to the carbon, and the way we name it is we add enol onto the end. So we've got ethanol, propanol, butanol, that sort of stuff. So the OH group takes priority over any alkyl groups like methyl, ethyl, anything like that, and over any halogens, and over any double bonds. So it's way more important than anything else we've looked at so far. So if we've got this parent chain here, I've got 5 carbons with an alcohol on the 2 position. So this is pentan-2-ol. Pentan-2-ol. So we've got to give the name. Sort of in the middle of the name there. You have to give the position of the OH. We only didn't give the position of the OH here in methanol and ethanol because there is only one position. It's on the 1 carbon. Just like haloalkanes, we can classify alcohols too. We're going to look at the number of carbon atoms that are bonded to the carbon which has the OH attached to it. So here this carbon is bonded to the OH, and this carbon itself only has 1 other carbon on it, so that is primary. This carbon has 2 others on it, so secondary, and this one has 3, so it's tertiary. So we're looking at the carbon that's bonded to the OH. So we'd name this propan-1-ol, and propan-2-ol, and 2-methyl-propan-2-ol. So don't forget the "and" bit in between. Here's an exam question, just like we looked at for haloalkanes, drawing the structural or constitutional isomers of C4H10O that are alcohols. So here they are. Physical properties like melting and boiling points, again, the same trend that we've seen before. The bigger the chain length, the higher the melting and boiling point. The reason for that is we've got stronger intermolecular attraction between the molecules, so more heat energy required to separate them. If we compared like propanol to propane, propanol would have a higher melting point or boiling point as opposed to that corresponding alkane, because that OH group gives us a special type of intermolecular bonding called hydrogen bonding, which you'll only look at next year, but just know that there's an extra type of bonding which makes this intermolecular attraction a little bit stronger and therefore harder to separate than just a plain old alkane. Solubility in water, so this is slightly different to what we've seen. The OH group makes alcohols polar. So as long as the carbon chain is quite small, like 1 to 3 carbons, then overall it'll be soluble in water, will have an overall molecular dipole. But as the chain length increases, that really big hydrocarbon chain actually dominates and reduces the overall polarity. So more than 4 carbons, they're less soluble in water and will form 2 layers like we've seen before. So for example, if I've got ethanol, which looks like this, there's just 2 carbons, so this polar part of the molecule is going to outweigh this little non-polar bit, and means that overall this is polar and will dissolve in water, forming just 1 layer. Whereas if I've got like hexanol, like this polar part with the OH is going to be dominated over by this big non-polar part of the alcohol, which overall makes this alcohol non-polar and not soluble in water. So you can see here up to butene, the solubility just drops. So only carbons 1 to 4 are actually soluble in water, and after that the solubility just plummets and will form 2 layers. So from pentanol onwards, you'll form 2 layers with water, whereas these ones would form 1 layer.